The purpose of this lab was to simplify a flexible beam system and create a second-order system model using a transfer function. This was accomplished using a flexible beam attached to a rotary servo motor which operated at different amplitudes and frequencies. Overall, it was found that as the frequency increases, the phase angle values drop.
For the procedure of this experiment, we first measured the strain gauge voltage at 5 different deflections of the beam to construct a calibration equation for the beam deflection. We used Simulink to measure the voltages in this experiment. We then measured the system response at specific frequencies and amplitudes. We applied the sinusoidal forcing method to this part in order to obtain the values of the phase angle and amplitude ratios. After that, we measured the response at random vibrations. The objective of this experiment is to make a comparison between finding the frequency response by using specific amplitudes and frequencies and by using random vibrations. By the end of this experiment, we can find the frequency response using only one test of a random vibration. For the first part of the results, we made a plot of the motor angle versus time along with the beam deflection versus time on the same plot for the 6 tests that we did. For each test, we determined the motor angle amplitude, beam deflection amplitude, amplitude ratio, and the phase angle. The phase angle was calculated using sinusoidal forcing method at specific frequencies, and it was also calculated using the zero crossing time between the input and the output.
So this is magnitude and phase of frequency response function using FFT and force response analysis. As we can see that the force response analysis lacks data points, hence FFT analysis is better than force response analysis. Here we see the magnitude and phase of frequency response function using FFT and force response analysis on a board plot. The analysis is the same as the previous one, that the FFT analysis is better because force response analysis lacks data points. Here we attempt to find the transfer function fit for the vibration data. So as you can see, here is the transfer function fit before adjusting for the natural frequency, damping ratio, and gain. The transfer function is given by the following mathematical expression. The natural frequencies corresponds to the peak of this vibration data. We can determine the damping ratio by looking at the relative height of these peaks. And the gain is calculated using the vertical misalignment. As you can see here we have a transfer function fit after we have adjusted for the natural frequency and damping ratio and by setting gain k equals 1. Here we see we have a transfer function fit of the data after adjusting for the natural frequency, damping ratio and gain. But this transfer function fit is only valid up till 10 Hz only. In order to mathematically encapsulate the transfer function which can describe the data up till a frequency of 30 Hz, we need to multiply the individual transfer function. But in the second term, we note that the numerator and denominator have been inverted. The reason for it is because the second peak is in the inverted direction as compared to the other peaks. Here we see a transfer function fit after adjusting for the natural frequency, damping ratio and setting k equals 1. We repeat the same analysis as we did for part 4 to find the final transfer function fit. Here we see we have a transfer function after we have adjusted for natural frequency, damping ratio and gain. Now our transfer function is accurate up till a frequency of 30 Hz.